This video is about single population hypothesis testing for population means. Our first test is called the z-test about population mean, and this particular test is performed if certain conditions are met. First, we are making inferences about a population mean and not a different parameter. Next, the population standard deviation is known. So for the variable that we are making inferences for, the standard dev of the entire population is known. Finally, because this is a z-test which is based on the normal distribution, the sampling distribution of the sample mean must be normally distributed, which means that either the variable itself is normally distributed or the sample size is large enough. And the test statistic that will serve as the basis for us to make a decision about the hypothesis is computed using this formula. It's basically converting the sample mean to a z-score using this formula. So that's x bar minus mu naught. This value is the constant in the null and the alternative hypothesis. And then we divide the difference by sigma sub x bar, or the standard dev of all possible sample means. And from sampling distributions, we know that if capital N over small letter n is large enough, or if the population is counted as an infinite population, then this is simplified as sigma over the square root of n. But if the population is finite, if capital N over small letter n is less than 20, then we will use a slightly longer version of the formula, which includes the finite population correction factor. So in the trash bag case that we have assessed earlier, we have already identified the null and the alternative hypothesis. So the null hypothesis states that mu is less than or equal to 50, while the alternative hypothesis states that the mean is greater than 50 pounds. Now, in order to assess the weight of evidence that we have, we will test these hypotheses using four values of alpha. So we have 10%, 5%, 1%, and 0.1%. Now, to confirm that the z-test for the population mean is the appropriate test to be performed, we will assess the assumptions or the conditions that were stated, which are required to perform the z-test for the population mean. So first, indeed, we are making an inference about a population mean. So in that particular case, we want to make a conclusion about the average breaking strength. Next, the sampling distribution in the trash bag case is approximately normal. We don't know the distribution of the individual breaking strengths of all the trash bags, but the sample size is large enough. And based on the central limit theorem, the sampling distribution of the sample mean is considered approximately normal. And finally, the population standard deviation of the individual breaking strength is known. That's 1.65. So based on all of those information, we confirm that the appropriate test is a z-test for the population mean. Now, as mentioned earlier, there are two methods that can be used in order to make a decision when performing hypothesis tests. First, we will perform the critical value method. And in this particular method, the rejection rule for a one-sided greater than alternative hypothesis is that we reject the null hypothesis if the test statistic that we will compute for exceeds the critical value. So if the test statistic that we compute for is equal to or less than the critical value, then our decision is the opposite. We will not reject the null hypothesis. Now, how do we determine the critical value? The critical value is a z-score that yields an area of alpha to its right. So for each value of alpha, there is a corresponding critical value that we will be comparing against the test statistic. So since we have four values of alpha, therefore we have 4 critical values as well that will be compared to the test statistic. So again, the critical values are z-scores whose area to the right is equal to alpha. So for an alpha of 10%, the critical value is 1.28 because the z-score 1.28 has an area of 10% to its right. Meanwhile, for an alpha of 5%, the critical value is 1.645. For an alpha of 1%, the critical value is 2.33. And finally, for an alpha of 0.001, the critical value is 3.09. All of these critical values can be obtained from the standard normal table. And again, these critical values were determined based on the values of alpha that we have set earlier at the start of the analysis. So these are the values that we will be comparing to the test statistic that we will be computing for in the next step. Now, to compute for the test statistic, we use the formula that was shown earlier. So again, we have the following information. The mu naught, that's the constant in the null and the alternative hypotheses, that's equal to 50. The sample mean based on a sample of 40 is 50.575. And the standard F of a population is known to be 1.65. So in this particular example, we use the shortened version of the formula for sigma sub x bar because we don't know the size of the population. We don't know how many trash bags there are in the population, but it makes sense to assume that it's a large number and that it keeps on increasing because the company will just keep on producing new trash bags, and therefore capital N can be assumed to be a large value. So computing for the test statistic, we will get 2.20, and this is what we will compare to the critical values. So going back to the critical values, our test statistic is 2.2, which is somewhere here. This test statistic exceeds the critical values for two values of alpha, right? So that test statistic 2.2 is greater than 1.28, and it's also greater than 1.645. Therefore, for these two values of alpha, we will reject the null hypothesis. However, for alphas 1% and 0.001, the test statistic 2.2 is less than the critical values. Therefore, according to the rejection rule, for these two values of alpha, we will not reject the null hypothesis. And the decisions are summarized here in this table. Again, the test statistic is only bigger than the critical values for alphas 10% and 5%, but not for 1% and 0.1%. That's why we only reject the null hypothesis up to 0.05. And based on the weight of evidence that was discussed earlier, this means that we only have strong evidence. We were able to reject up to 5%. Therefore, we have strong evidence to support the alternative hypothesis. And that's what we will use in order to make an interpretation of the results. There is strong evidence to support the claim or to support the alternative hypothesis that the average breaking strength of all the trash bags exceeds or is greater than 50 pounds. So we have strong evidence to support the alternative hypothesis, which is that mu is greater than 50 pounds. So that's the procedure when using a critical value method. Now, if we use the p-value method, the rejection rule is a bit different. For the p-value method, the rejection rule states that we reject the null hypothesis if the p-value is less than alpha. So instead of looking for a critical value, we will compute for a p-value and then just directly compare that to alpha. And if the p-value is less than alpha, then we can reject the null hypothesis. Or in other words, if the p-value is greater than or equal to alpha, then we will not reject the null hypothesis. So using the same example, our test statistic is 2.2, and therefore the p-value is the area to the right of this test statistic. So the p-value is a probability. And for one-sided greater than alternative, the p-value is an area to the right of the test statistic. So in this particular example, the p-value is the area to the right of 2.2. And this area can be easily obtained either through the standard normal table or using the normal distribution function in most calculators. So whichever approach you use, you will get a p-value of 0.0139. And this is what we will compare to the four values of alpha. And our rejection rule again states that if this is less than alpha, then for that value of alpha, we reject the null hypothesis. So again, we have here a summary of the results. Our alpha is 0.0139, which is less than 10% and 5%, but it's greater than 1% and 0.1%. Therefore, for these two values of alpha, we reject the null hypothesis. And for these two values of alpha, we do not reject the null hypothesis. So again, the results are similar whether you use a critical value method or a p-value method. For critical value method, it includes identifying critical values, but for the p-value method, it involves looking for a p-value in order to make a decision. And therefore, our interpretation should be the same. There is strong evidence that supports the alternative hypothesis, which states that the average breaking strength of the trash bags is greater than 50 pounds. Or in other words, there is strong evidence that supports the claim that the trash bag of the company is the strongest in the market. So that's how we perform a hypothesis test for a one-sided greater than alternative. Now, how does it differ from a one-sided less than alternative? So let's now look at the payment time case. So in the payment time case, again, we've identified the null and the alternative hypotheses earlier. So again, the null hypothesis states that the mean is greater than or equal to 19.5 days, while the alternative hypothesis states that the mean is less than 19.5 days. So in this example, we will also use four values of alpha, 10, 5, 1, and 0.1%. And we will also confirm that the z-test for the population mean is the appropriate test. So again, we are making an inference about a population mean. In this case, we are looking at average payment time. In this case, we can also say that the sampling distribution is approximately normal. We don't know the distribution of the individual payment times, but our sample size is 65, and this is large enough. Therefore, the sampling distribution, according to the central limit theorem, is approximately normal. And finally, the population standard deviation is also known. In this case, that is equal to 4.2. And therefore, again, we have confirmed that a z-test for the population mean is the appropriate test to be performed in this example. Using critical value method, the rule is now a bit different. So for one-sided less than alternative hypothesis, the rejection rule is that we reject the null hypothesis if the test statistic is less than the critical value. So compared to what we got earlier, for one-sided greater than, remember, we rejected the null hypothesis if the test statistic exceeded the critical value. But since this is one-sided less than, the rejection rule is to reject the null hypothesis if the test statistic is lower than the critical value. Apart from that, another difference is that the critical value for one-sided less than alternative is the z-score with an area of alpha to its left. Okay, so the area is now to the left instead of to the right because this is a one-sided less than alternative. So for this particular example, we have the following critical values. So again, the critical values are the values of z whose areas to the left are equal to alpha. So for an alpha of 10%, The z-score or the critical value is negative 1.28 because the z-score negative 1.28 has an area of 10% to its left. Meanwhile, for an alpha of 0.05, the critical value is negative 1.645. For an alpha of 1%, the critical value is negative 2.33. And finally, for an alpha of 0.001, the critical value is negative 3.09. If you compare these to the critical values we had earlier, the only difference is the sign. These are negative because, again, this is a one-sided less than alternative. And the critical values are negative in this particular example. And the z-scores are also the same. The absolute value of the z-scores are the same because, again, the values of alpha that we are using are the same as the ones we used earlier. So these are now the values that we will compare to the test statistic that we will compute for. So in the payment time case, the test statistic is again computed using the same formula. Here, the sample mean is 18.1077. Mu naught, the constant in the hypothesis, is 19.5. Sigma, that is known, that is 4.2. And the sample size is 65. So like the first example, we use the shorter formula for the denominator because the population here is considered to be infinite. So we don't know the exact number of payment times in the population, but it is reasonable to assume that it's a large number which keeps on increasing. So payment time keeps on increasing every time someone pays. And therefore, it is reasonable to assume that it's infinite, and we can use the shorter version of the formula. So computing for the test statistic will give us a test statistic of negative 2.67, which is the value we will compare to the critical values that we have here. Now, where is the test statistic compared to the critical values? Our test statistic is negative 2.67, which is somewhere here in this area. And therefore, this test statistic is inside the rejection areas of several values of alpha. So the rejection areas are basically the areas to the left of the critical values. So remember, we reject the null hypothesis if the test statistic is less than the critical value. So the areas to the left of the critical values can be said to be rejection areas. And the test statistic is inside the rejection areas of alphas 10, 5, and 1%. Okay, but the test statistic is greater than the critical value for 0.001. Therefore, we have here a summary of the decisions. We reject the null hypothesis for alphas 10, 5, and 1%, but we do not reject the null hypothesis for an alpha of 0.001. And therefore, since we are now able to reject the null hypothesis at an alpha of 1%, our weight of evidence is very strong. There is very strong evidence to support the claim that the average bill payment time of all the customers under the new bill payment system is now less than 19.5 days. So we have enough evidence to support the alternative hypothesis. Specifically, there is very strong evidence to support that. So that's how we perform a critical value method for a one-sided less than alternative. Now, using the p-value method, steps 1 to 3 would be the same. So we now skip to step 4. And for one-sided less than alternative using the p-value method, the rejection rule is not affected. We also reject the null hypothesis if the p-value is less than alpha. What differs now is how to compute or how to determine the p-value. Since this is a one-sided less than alternative, the p-value is no longer the area to the right of the test statistic, but the area to the left of the test statistic. So earlier we computed for the test statistic and we got negative 2.67. So the p-value is now the area to the left of negative 2.67. And when you compute for that, you will get 0.0038. So you can get this again either from the standard normal table or using the normal distribution functions in your calculator. You will get the same probability, which is 0.0038, and this is the p-value. And this is what we will compare to the four values of alpha. If this is less than alpha, then we will reject the null hypothesis. So using the same set of values for alpha, 0.0038, the value, the p-value is somewhere here. Therefore, we reject the null hypothesis for alphas 10, 5, and 1% because the p-value is lower than those values of alpha. But for an alpha of 0.001, we do not reject the null hypothesis because 0.0038 is slightly bigger than 0.001. And therefore, our interpretation should be the same. There is very strong evidence to support the alternative hypothesis, which states that the average bill payment time of all customers under the new payment system is now less than 19.5 days. So that is the procedure in performing hypothesis tests involving one-sided less than alternative. Finally, for a two-sided not equal to alternative, like the Valentine's Day chocolate case, we've identified earlier that the null and the alternative hypotheses are the following. We will use the same values for alpha, 10, 5, 1, and 0.1%. And then step 3, we assess if the z-test for the population mean is still the appropriate test. So again, in this particular example, we are making a conclusion about a population mean. Specifically, the mean we are talking about pertains to the average number of boxes ordered. So that is a population mean. Next, the sampling distribution is approximately normal. So again, we don't know the distribution of the orders, but the sample size of 100 is large enough, and therefore the sampling distribution is approximately normal according to the central limit theorem. Finally, the population standard error is also known, that's 40. And based on this information, we confirm that the z-test for the population mean is the appropriate test. Now, for two-sided not equal to, when using the critical value method, we will now have two critical values for each value of alpha. Since this is two-sided compared to the two previous examples, we will now have two critical values for every value of alpha. And those two critical values are, first, the z-score with an area of alpha over 2 to its left, while the other one is the z-score with an area of alpha over 2 to its right. And we reject the null hypothesis if the test statistic is less than the negative critical value or if it's greater than the positive critical value. Or in other words, the rejection areas are areas to the left of the negative critical value and the area to the right of the positive critical value. So in this particular example, we have the following pairs of critical values for the four values of alpha. So for the alpha of 10%, our critical values are positive and negative 1.645. So remember, that's alpha of 10%. So split that to 2. You have 5% here and you also have 5% here, which gives us positive and negative 1.645. For an alpha of 5%, split that to 2, you have 0.025 for both sides, and the corresponding critical values would be positive and negative 1.96. For an alpha of 1%, the critical values are positive and negative 2.575. And finally, for an alpha of 0.0005, 0.001, split that to 2, you have 0.0005 in both sides. And the corresponding critical values will be positive and negative 3.29. So the rejection areas are again these areas to the left of the negative critical values and the areas to the right of the positive critical values. So if the test statistic falls in any of those two rejection areas, then we will reject the null hypothesis. Now, computing for the test statistic using the same formula, we will get -1. So we have the same formula. This is x bar, this is mu naught, this is the constant in the null and alternative hypothesis. This is sigma, and this is the sample size. Again, in this particular case, we use the shorter version for the formula for the denominator because we don't know the population size. Okay, and in this case, we assume that it's a large number. So the test statistic is -1, and now we locate that compared to the 4 pairs of critical values. The test statistic is somewhere here, -1. And the test statistic is not inside any of the rejection areas. It's not inside the rejection areas for 5%, for 10%. So for 10%, remember the critical values are positive and negative 1.645, and the test statistic is not inside that. And therefore, for all other values of alpha, the test statistic is also not inside their rejection areas. Therefore, our summary of results will look something like this. For all 4 values of alpha, we will not reject the null hypothesis, and therefore, there is insufficient evidence or there is not enough evidence to support the alternative hypothesis or the claim that the average order quantity in all the stores is not 330 boxes. So we don't have sufficient evidence to support this. We don't have sufficient evidence to support this, so we still assume that the average is still equal to 330. So that is the practical implication of this result. Now, how will it differ if we use the p-value method? So in the p-value method, what will differ will be how to compute for the p-value. The rejection rule is the same. We reject the null hypothesis if the p-value is less than alpha. But again, the difference will now be in computing for the p-value. So now the p-value is either the area to the left or to the right of the test statistic multiplied by 2. Because remember, this is two-sided. Now, which side do we compute for? In this particular case, since our test statistic is negative, what we will get is first is the area to the left of the negative test statistic. In this case, according to the standard normal table or to our calculators, that's 0.1587. And we will multiply that by 2 to get the p-value, which is 31.74%. So again, we get the area first to the left of the test statistic because our test statistic is negative. But in a different example, which is still two-sided, not equal to, but the test statistic is positive, the p-value will first be the area to the right of the positive test statistic and then multiply that by 2. Okay? So the p-value is 31.74%, which is greater than all of these 4 values of alpha. Therefore, for all the 4 values, we do not reject the null hypothesis. And therefore, we have the same interpretation that there is not enough evidence to support the claim that the average for all the stores is not 330 boxes. Okay? So those are the differences in performing a z-test for the population mean for the 3 types of hypotheses: one-sided less than, one-sided greater than, and two-sided not equal to. And also the differences between critical value and p-value methods for those 3 different types of hypotheses. So we have here a summary of the differences between them, which is, again, dependent on the type of the alternative hypothesis that is being tested.